Picture this. Late afternoon. The light is golden, washing across rooftops, through tree-lined avenues. There is a faint hum overhead. Neighbors glance up, curious but not alarmed. From maybe 200 feet up, a small craft hovers, steady. From it, a thin tether descends. Encased in a shell that is biodegradable, a parcel glides down, making a precise landing on a pad. A little square pad outside a clinic, perhaps, or a pharmacy. It takes no more than seconds. No sirens, no horn blasts, no traffic snarls. Just engineered choreography. Delivery made, craft ascends, vanishes, already bound for its next mission. What I have just described is not fantasy. It is a picture of what many companies are building toward, what some are already doing. It is the modern supply chain gaining a third dimension, the sky. Why aerial logistics? The case for skyborne delivery. Let us begin with the why. Why this is happening now and why it matters. A. Rising expectations in a just-in-time on-demand world. We live in a time when patience is short. Consumers expect what they want when they want it. Same-day deliveries, urgent orders, medical needs at a moment's notice. Whether it's diagnostic samples from labs, organs, critical medicine, or e-commerce parcels. The pressure is high. A delay of even an hour can mean the difference between life and death in healthcare. In commerce, delayed deliveries mean loss of trust, cancellations, returns. Vulnerabilities in traditional logistics. Traditional logistics depend on roads, rails, bridges, infrastructure that is subject to breakdown. Floods, earthquakes, wars, pandemics, climate change, all can disrupt ground transport. Congested roads, traffic jams, environmental constraints, infrastructure bottlenecks. As much as we have built, as advanced as many ground systems are, they have limitations. What aerial delivery brings to the table. So aerial delivery offers some powerful countermeasures. It bypasses congestion, making direct point-to-point routes possible. A drone doesn't care about traffic lights or jammed intersections. It shrinks delivery cycles for time-sensitive or perishable payloads, vaccines, blood, medicines, or even food in remote areas. It can reduce emissions, especially in dense urban cores, where many short van trips are inefficient and polluting. It offers reach into remote or austere locations where roads are poor or ground travel is dangerous or slow. However, let's not fool ourselves. Turning the sky into infrastructure is not easy. It requires precision engineering, aviation-grade safety, regulatory alignment, community acceptance, hard software and hardware, discipline and operations. Anatomy of a drone delivery network. What does a drone delivery network look like under the hood? What components must work well for the system to be safe, reliable, scalable? Here are the key elements: airframe and propulsion, multi-rotors, nimble, good for vertical takeoffs, landing, good hovering ability, but energy limited. Fixed wing, efficient, good for forward flight and distance, but needs space for takeoff and landing. Hybrid VTOL combines vertical lift with efficient forward flight, the holy grail for many cargo drone missions, autonomy and avionics, navigation systems, GPS/GNSS, IMUS, airspeed sensors, sometimes optical or visual odometry. Redundancy, multiple motors and controllers, backup communication links, safety fallbacks, parachute or controlled descent if things go wrong. Ground infrastructure, launch/recovery systems, vertical pads, gantries, runways depending on the drone type, distribution centers, warehouses, inventory, packaging, cold chain for temperature sensitivity, charging stations or battery swap systems for high utilization, operational control, communication links, cellular, radio frequency, encrypted, reliable, fleet management, scheduling, routing, monitoring health, handling failures, remote pilots or supervisors, especially under BVLOS, beyond visual line of sight, and possibly handling multiple drones at once. Safety and compliance, Detect and avoid systems, geofencing. Risk assessments tailored to local population, density, terrain, weather. Working closely with aviation regulators for required waivers, certifications, approvals. Customer experience. For healthcare, integration with medical records, standardized packaging, tracking. For retail, precision delivery, even tethered delivery or lowering payloads without landing. Notifications, tracking, estimated delivery times, etc. Every company works all these pieces, but the way they optimize them depends on their mission. Medical, defense, urban parcel delivery, remote locations, contested environments. The four players, Zipline, Volansi, Matternet, and Grid Aero. Now let's introduce the four companies and see how each handles the stack differently, how their mission shapes how they build. Zipline life-saving speed. Origins and mission. Zipline started with an explicit focus on medical delivery, blood, vaccines, critical medicines, things whose timely delivery matters not just for convenience, but for life. Their moral clarity in that mission has shaped everything. Their engineering, their safety culture, the route to scale. Aircraft and delivery techniques. They have developed platforms that emphasize speed, range, precision. One of their recent innovations is a tethered delivery system. Instead of landing, the craft lowers packages with a tether. This reduces noise, minimizes the risk of landing in uneven terrain, makes it safer over populated or constrained landing areas. Regulatory and U.S. expansion. Zipline has been at the forefront of seeking and securing FAA waivers, approvals, the kind that allow more advanced operations, BVLOS, operations over people, etc. Their expansion in the U.S. is bolstered by a face-to-face approach, local partnerships, data, safety records. User experience. For a clinic or hospital, the workflow begins with requesting supplies. From that moment, inventory, packing, pre-flight checks, routing, payload balancing, all software orchestrates that chain. Then the flight, precise drop or tether, confirmation, etc. Over time, Zipline aims to densify coverage so that many communities are within, say, 15 to 45 minutes of a distribution node. Volansi, long-range VTOL for harsh and remote missions. Mission and niches. Based in San Francisco, Volansi focuses on longer-range hybrid VTOL cargo drones. Their strength lies in operations that are remote, difficult, maybe dangerous for ground logistics or conventional aviation. Use cases. Defense resupply is a key arena for them. What if forward units need batteries, spare parts, medical supplies, where road convoys are risky? Also, remote industrial applications, oil/gas platforms, mining outposts, rural infrastructure, environmental/inspection work. Vehicle design. Their aircraft are built to be rugged, with modular payload bays, reliable components, efficient VTOL to transition into cruise flight. That hybrid approach permits vertical departure and landing yet efficient cruise over distance. Operational model. Volansi emphasizes field support, modularity, predictable performance in adverse conditions, software management, safety margins, training for variable weather, etc. Matternet, urban arteries and healthcare partnerships, focus on urban environments. Matternet is designed for the city, not for long flights over deserts or seas, but for rooftop to rooftop, hospital to hospital, or micro-fulfillment center to pharmacy. Short hops, predictable high-frequency flights. Institutional partnerships. Matternet has worked closely with healthcare providers, UPS Flight Forward, hospitals. These partnerships have helped shape operations, what kind of payloads, what regulatory clearances, what landing infrastructure is acceptable, all that. City considerations. Urban airspace is constrained. Buildings, people, noise, safety concerns. Matternet tuned its aircraft and landing/launch systems accordingly. Quiet takeoff and landing pads, standardized infrastructure, careful flight corridors, predictable schedule windows. Outcomes. For hospitals, labs, day-to-day medical work, This means faster diagnostic turnaround, fewer delays in interfacility transfers. For the public, if done well, these flights become routine, quiet, safe, so much so that people barely notice them. Grid Aero, the stealth scout. Emerging player with a military defense edge, Grid Aero is a newer entrant. What sets them apart is a focus on contested logistics, places where resupply by conventional means is risky, where detection or attack is possible, or communications are unreliable. Lifter light platform. Their cargo drone concept is designed to be quieter, stealthier, lower signature, both acoustic and radar, designed for long range, but with emphasis on survivability and autonomy in the face of adversity. Operational requirements. Being able to launch from minimal infrastructure, being able to fly when comms are limited, fallback autonomy, smart route planning to exploit terrain, avoid exposures. Mission fit reflects the overlap between defense and commercial. Lessons from military context feed into commercial robustness and vice versa. Regulatory reality, FAA, BVLOS, traffic management. All of this does not exist in a legal vacuum. The rules matter. The air is regulated tightly. Safety, public trust, and legal permissions are critical gating factors. FAA Part 1, '07, the baseline rules for small unmanned aircraft systems. Visual line of sight, weight limits, pilot certification. Most simple drone operations begin here. Waivers and special authorizations. For more advanced operations, flying at night over people, BVLOS, beyond visual line of sight. These require special permissions, safety cases, lots of data. Type certification, production certification. As companies scale, they need formal aircraft certification to sell at scale, ensure safety standards. Remote ID, UTM, Unmanned Aircraft Systems Traffic Management. A way for aircraft to identify themselves, for authorities to track them, for coordination among many aircraft, drones, helicopters, airplanes, especially in shared airspace. Noise, community engagement, land use. Even with perfect engineering, people matter. If drones are too loud, fly over neighborhoods unpredictably, have privacy-concerned sensors, the public may push back. Noise standards, flight path transparency, predictable schedules, all help. Safety by design. Safety is not optional. The promise of aerial logistics depends on convincing people, users, regulators, neighbors, that it is safe, reliable, and trustworthy. Some of the practices that make this possible: redundancy in hardware and software, multiple motors, backup sensors, graceful failure modes. A motor fails, but plane still flies. Control link drops, but fails over to autonomous flight plan. Conservative routing and altitude buffers. Avoid flying over dense crowds when possible. Use corridors that are less populated. Avoid steep approach trajectories. Precision delivery methods, tethered offloading, parachute drops, lowering payloads rather than landing, minimizing disturbance to surroundings. Weather and terrain intelligence, gusts, updrafts, wind tunnels in city canyons, terrain features, rules to abort a mission if conditions exceed thresholds. Maintenance and data monitoring, condition health monitoring, pre-flight and post-flight checklists, using simulation or digital twins to predict stress and fatigue. Community engagement, letting people know when and where flights will happen, demonstrating operations, transparency about failure rates and incidents, noise testing, support for public concerns. Economics, how this becomes viable. Technology and regulation are necessary but not sufficient. For aerial logistics to be more than novel pilots, the economics must work. Here are the levers. Utilization. The more flights an aircraft can make each day, the more you spread fixed costs, aircraft purchase, maintenance, regulatory compliance. Idle aircraft are expensive. Network density. Fewer, more frequent routes around distribution hubs reduce transit time and cost. If you can have many delivery points in a dense area, you amortize infrastructure. Payload value. High-value, time-sensitive payloads, medical, defense, urgent spare parts, can justify premium delivery fees. As costs fall, lower value or non-urgent shipments become possible. Labor costs. Right now, humans are often involved, pilots, supervisors. As regulations allow operations under beyond visual line of sight, one pilot might supervise multiple drones. Automation helps reduce human labor per delivery. Infrastructure scaling. Standardized launch/recovery pads, battery swap or fast charging, modular systems. Those reduce per-flight marginal costs. Regulatory clarity and incentives. Incentives for clean operations, tax breaks, subsidies for medical or remote operations, clearer pathways for certification. These shape the cost curves. Each of the four players uses a different economic model. Zipline aims for dense medical networks. Matternet focuses on many short hops in urban areas. Volansi covers distance and payload. Grid Aero may have fewer but more dangerous or specialized missions. Case studies. A day in the life. To make all of this concrete, let me walk through four imagined but representative case studies that illustrate how these systems work in practice. Case Study 1. Zipline's medical network at dawn. It's early morning. A distribution center, perhaps in a rural region or semi-urban zone, is coming to life. Orders have come in overnight from clinics, pharmacies, rural hospitals. Items like blood units, vaccines, critical medicines, insulin. Warehouse staff begin restocking. Warehouse software cross-references inventory. Flags needed supplies. Meanwhile, a Zipline aircraft is being prepared. Battery health checked, control systems tested, communications links verified, payload packed with temperature control as necessary. The flight plan is computed. Departure point, route over lower population density, avoiding schools or other sensitive areas. Wind, weather forecast, possible transient flight restrictions considered. A tethered delivery zone identified. Perhaps a pad at a small clinic. The craft lifts off, cruises, approaches the destination, hovers, lowers the payload using the tether. Sensors verify safe release. The recipient confirms with their system. The craft ascends, reverts course to next mission, or returns to base for battery swap or maintenance. Multiple flights scheduled that morning, all coordinated to optimize utilization and minimize risk. This works quietly, quickly, with minimal disruption. And because of trust, approved regulations, infrastructure, people accept the occasional hum overhead as part of daily life. Case Study 2. Matternet's Urban Health Loop. In a dense city, perhaps one where traffic is unpredictable or congested, multiple hospitals, clinics, labs are distributed across different neighborhoods. Lab samples need fast transport. Some medications must move rapidly between centers. Matternet has established landing and launch pads on hospital rooftops or on top of medical centers. Small, controlled, fenced areas, equipped with power, charging, temperature control, perhaps staff zones. A nurse loads a small payload, a lab sample or a set of medications, into a standardized canister, scans a code. The Matternet aircraft is summoned. A short flight, just minutes, over city rooftop corridors. The city has approved specific flight corridors, altitudes, flight windows. Noise minimized by design. On arrival, the payload is automatically identified, removed. The return flight proceeds. What used to take 30 to 60 minutes on congested roads with couriers or small vehicles now takes minutes. Diagnostic cycles accelerate. Patients benefit. Hospitals reduce ground courier costs. The public sees fewer delivery vans struggling in traffic. Quieter rooftops. Less pollution. Case Study 3. Volansi for remote or defense missions. Imagine a remote industrial site, a platform at sea, or a remote subarctic research station, or a forward operating base for defense. A component or urgent replacement part is needed. A helicopter is an option, but extremely costly and weather sensitive. Logistics chains are long, fuel expensive, risk of ground or sea transport high. Volansi is called upon. A coastal launch site is prepared. The aircraft is loaded with a modular payload. The flight plan covers a long over-water or over-terrain route. Using its VTOL vertical takeoff, it lifts off from the launch pad, transitions to forward flight. En route, careful route planning maintains safety, avoids bad weather, reserves extra battery or power margin for contingencies. At the destination, the landing or delivery pad is prepared. The craft lands, releases the part, returns, or moves on. The industrial site resumes operations sooner. Cost and risk lower than helicopter or ship shipments, depending on distance. Case Study 4. Grid Aero and Contested Logistics. In an environment where conventional logistics are not just slow, they are dangerous. Maybe in a remote region with hostile actors or degraded infrastructure, or where aerial detection and anti-aircraft is a concern. A forward team needs medical kits and batteries. A convoy could be detected, ambushed, or delayed. Communication links are spotty or could be jammed. Roads are unreliable. Grid Aero's lifter light is readied in a concealed clearing. The mission is preloaded. Route exploiting terrain masking, flying under radar detection when possible, using autonomy where communications are untrusted. It launches at dusk, taking advantage of low light. As it flies, comms drop. Autonomy kicks in. At the destination, the drone lowers or drops the payload quickly, perhaps via tether, perhaps via a low-altitude release. The team confirms receipt. The drone returns via a different path to reduce pattern predictability and risk. The mission succeeds with minimal exposure. This kind of operation stretches every piece of the system: stealth, reliability of autonomy, safety backups, aircraft design, rapid response. What makes this possible? Technology deep dives. Let's examine certain technical advances that have pushed aerial logistics from idea to reality. VTOL hybrids. They offer some of the best of both worlds: vertical lift for takeoff and landings where ground space is constrained, cruise efficiency like fixed-wing craft when flying longer distances. The trade-offs are complexity, more moving parts, more potential failure points, weight penalties. But for many of these missions, long-range, off-road, remote, they make sense. Tethered precision delivery. Instead of landing, the craft hovers and lowers cargo with a tether. Why is that attractive? A number of reasons: less risk in landing, uneven terrain, obstacles, people are all concerns. Less noise at ground level. Rotors are farther away when lowering, with less destructive rotor wash. Greater flexibility in where deliveries can be made. Smaller pads, obstacles around. Better safety near people and infrastructure. Battery innovation. Batteries are a big limitation. Energy density, cycle life, thermal stability, recharge time. But progress is being made. Better chemistries, better thermal management, battery swap stations or modular battery packs, second life use of batteries, recycling. All that matters. Autonomy, sensor fusion, resilient estimation. Flying in variable weather through urban canyons with intermittent communications requires sophisticated sensing. GNSS, IMU, barometer, visual cameras, or LIDAR, radar. Redundancy helps too. Software systems that can fuse these inputs and maintain stable flight even when some inputs are degraded. Fleet orchestration. One drone is interesting. A fleet is transformative. Coordinating many flights means scheduling, routing, balancing airspace, managing noise windows, managing battery use, managing maintenance cycles, edge computing, cloud coordination, real-time telemetry, predictive analytics, they all enter. Community, social license, environmental accounting. Technical success alone will not make this real in everyday life. Communities must accept it, environment must benefit, societal concerns must be addressed. Noise. Even if drones are quieter than helicopters, people hear them. High-frequency rotor noise travels. If flight paths over neighborhoods are frequent, annoyance builds. Designs are improving. Approach path planning helps. scheduling windows, routing over less sensitive zones, privacy, cameras, sensors could gather sensitive imagery, transparency, data minimization, clear policies, compliance with legal frameworks are essential. Visual presence. Novelty wears off, but if drones are ubiquitous, overhead, people must trust that safety is real. Trust becomes as important as the engineering. Equity. It's important that benefits reach underserved communities, rural areas, medically underserved zones, food deserts, not just wealthy suburbs or dense urban cores. Public policy can subsidize essential flights or mandate access. Environmental footprint. Emission savings are real but depend on how electricity is generated, battery life cycle, how frequently the drones fly, and how large they are. Also, infrastructure. If many stations need construction, or if battery disposal becomes a problem, that can offset gains. But the potential is strong. In dense urban short routes, drones likely beat vans on emissions and speed. Regulatory and risk landscapes, what's holding back? Broader scale. Even as technical and operational advances accelerate, several critical limiting factors remain. BVLOS norms. Not universal, many countries/states still restrict beyond visual line of sight flights. That limits range, utility, efficiency. Type certification bottlenecks. Costly long trails of testing. For many aircraft designs, getting full type certifications is expensive and slow. UTM/air traffic integration. As skies get busier, coordinating drones, helicopters, small aircraft, airplanes becomes complex. Digital traffic management systems are necessary but still under development. Interoperability, real-time data sharing, dynamic flight restrictions, all must mature. Liability and insurance. Who pays when something goes wrong? If a drone causes damage or drops a package inaccurately or has a malfunction, who is responsible? Clear liability frameworks are needed. Community pushback. Noise, privacy, safety concerns may lead to local regulation or resistance. Without active listening and engagement, projects may stall. Infrastructure costs. While drones may reduce some costs, launching and landing pads, distribution centers, battery swap stations, charging, specialized warehouses, all cost money. Permitting, land use, zoning, power supply may be challenging. Battery limitations and weather. Extreme weather, high winds, rain, snow, fog. These remain big challenges. Battery performance suffers in cold. Charging infrastructure may be unreliable in remote sites. Looking forward, what will unlock the next leap? What breakthroughs, policy shifts, or investments will shift aerial logistics from promising pilots to widespread routine service? Normalization of BVLOS approvals, regulatory certainty about BVLOS flights will unlock many of the current constraints. If aviation authorities set rules and let operators follow them instead of case-by-case waivers, scale becomes possible. Standardized UTM systems. A reliable traffic management system for unmanned aircraft will help coordinate, reduce risks and conflicts, enable efficient routing and conflict avoidance. Battery and power innovations. Better energy density, hybrid or alternate power sources, faster recharging or battery swapping, robust battery life cycle management, noise reduction and rotor aerodynamic innovations, designing quieter rotors, better approach angle designs, shielding, damping. These will reduce barriers in urban zones. Modular and affordable launch/micro hub/vertiport designs. If small rooftops, parking garages, unused parcels can be converted into drone pads in safe, affordable ways, then infrastructure cost per site falls. Policy alignment and incentives. Municipal, state, national policies that offer incentives for medical or remote deliveries, subsidies, tax credits, grants, public procurement favoring aerial delivery in certain contexts, transparent public engagement, demonstrations, community meetings, pilot projects where people can see, experience, and understand the trade-offs. Open data on safety, noise, incidents. Cross-sector collaboration. Partnerships between government, industry, health systems, defense, academia, sharing data, safety lessons, best practices. Differentiation and strategic positioning, how the four compare. To understand the landscape, it helps to see how Zipline, Volansi, Matternet, and Grid Aero each occupy different niches. Their missions, aircraft, and strategies are not interchangeable. They are differentiated. Company strengths/niche key. Missions what they prioritize. Zipline, system-level integration, medical healthcare focus, regulatory wins, tethered delivery, dense network effects. Medical supply, clinics, rural hospitals, urgent deliveries, speed, reliability, safety over people, low margin on high value, building trust and regulatory precedent. Volansi, long-range hybrid VTOL, remote operations, industrial, defense, rugged use cases, defense resupply, remote infrastructure, offshore, mining, research, payload capacity, range, robustness, field deployability, Matternet urban precision, partnerships with hospitals, institution-based routes, micro-fulfillment, lab sample transfer, hospital to hospital, rooftop corridors in cities, frequent short flights, reliability, integration with health systems, low public disruption, Grid Aero, stealth/contested logistics, resilience, autonomy under constraint, defense missions, missions in risky or degraded environments, forward operations, acoustic/radar signature minimization, autonomy, route stealth, survivability. They are complementary rather than purely competitive, in many cases, where one lags another fills a gap. Over time, some of their domains may overlap more, but for now, the differentiation helps move the broader field forward by addressing different pain points. What it means for different stakeholders. Let's consider how this transformation touches various stakeholders: patients, clinics, health systems, faster delivery of critical supplies, better access in remote or underserved areas, more reliable supply chains, potentially lower cost, more resilient service when roads are impassable or infrastructure compromised, communities and cities, less road congestion, fewer delivery trucks idling in dense neighborhoods, potential for lower emission, quieter delivery, cleaner air, but also the need to manage impact, noise, airspace oversight, land use for pads, defense/government/disaster response, agility in offering supplies where needed, minimizing risk to personnel, delivering in austere or contested zones, improving resilience in disasters or war zones, businesses and e-commerce, improve speed, potential cost savings if aerial networks scale, new service models, competing on quick delivery becomes more feasible, but also new regulatory and operational challenges. Environmental advocates/regulators, potential to reduce carbon and local air pollution, but need to ensure environmental costs, battery, infrastructure, noise are not overlooked. Ensure equitable access. Avoid creating new burdens. Challenges, trade-offs, and potential risks. While the promise is strong, there are trade-offs and risks. Some we have already touched on, but worth enumerating. Safety incidents, mechanical failure, software bugs, communication loss. Even with redundancy, risk remains. One highly visible incident can set public opinion back. Privacy and surveillance concerns. Cameras, sensors may be misused or appear so. Public skepticism may rise if transparency is lacking. Noise pollution. Even quiet drones make noise. Frequency, timing, and location of flights matter. Over time, annoyance can grow. Regulatory failures or misalignment. If regulations are inconsistent, from one city to another or one state to another, scaling becomes hard. Some places may block or overly restrict drone paths. Infrastructure bottlenecks, power supply, space for pads, zoning, real estate for distribution centers, grid capacity for charging. Economic risk if demand does not keep pace. If usage is low, Cost per delivery stays high. Investors and companies may pull back. Battery supply and environmental externalities. Sourcing raw materials, recycling, disposal, energy mix if electricity is coal-powered, environmental benefit is reduced. Battery degradation in harsh environments. Cybersecurity threats. Communication links can be attacked or spoofed. GPS can be jammed or spoofed. Drones themselves could become targets. Equity concerns. If aerial logistics only serve wealthy areas or high-margin operations, underserved communities may see little benefit. Also, jobs displaced, couriers, small vehicle drivers, need attention. The bigger picture, how this changes logistics and supply chains fundamentally. What we are seeing is not simply adding drones to existing networks. The sky is enabling a new layer of logistics. It shifts thinking about where inventory is stored, how quickly items can be moved, what kinds of service levels are possible, and how resilient systems can become. Inventory location becomes more nimble. With fast aerial delivery, fewer local warehouses may be needed, or at least smaller ones. We might see more micro-fulfillment centers or medical caches. Redundancy and resilience improve. If ground routes fail, road blocked by flood, bridge down, roads impassable, air routes can serve as backups. New business models emerge. Pay premiums for urgent delivery, subscription models, medical drones as public health infrastructure, defense supply being partially offloaded to autonomous systems, even delivery on demand from stores or restaurants with drones. Urban form and planning shift. Roofs become important. Landing pads, charging stations, micro-hubs, vertiports. Zoning, building codes may change to accommodate drone infrastructure. Integration into digital infrastructure. Supply chain systems, health systems, corporate enterprise systems will need to integrate drone-based logistics as standard. Tracking, APIS, billing, compliance. Global reach potentials. In many developing or remote areas where roads are limited, bridges few, geography challenging, aerial delivery may be not just faster, but transformative. For example, delivering vaccines to remote clinics, delivering test kits, bringing supplies during humanitarian crises. Looking ahead, what will make the sky supply chain ordinary? What will it feel like when aerial logistics move from novelty to ordinariness? Some predictions, some hopes, schedules like mail trucks. Aerial delivery routes may run at certain times of day. People will know roughly when to expect flights, say early morning medicines, afternoon e-commerce drops. Standard pads and vertical ports, parking decks, building roofs, small modular pads, safe, inexpensive, perhaps community-shared pads. Transparent flight paths and apps. You open an app, see a small aircraft on its route, know when it passes near your place. Remote ID systems in place, perhaps citizen oversight or open data about noise or incidents. Regulations harmonized across jurisdictions. States, cities, federal rules aligned, so scale becomes routine. Affordability drops. As utilization increases, hardware improves, labor costs fall, regulatory cost per flight declines. Then drone delivery becomes competitive, not just for high-value or urgent items, but for many everyday items. Environmental benefits greater, more electric power in grids, battery recycling robust, simple drone deliveries reduce van traffic, improve local air quality, less traffic congestion. Social acceptance widespread. People get used to humming overhead, novelty fades, trust in safety, expectations that certain medical or emergency deliveries happen by air. Why this matters now? Timing and convergence. Why are we seeing this moment? Several converging trends. Hardware catching up, batteries better, motors more efficient, materials lighter, sensors more capable, hybrid VTOL designs more mature, autonomy improving, software and network tools more mature, fleet management, sense and avoid, navigation, air traffic integration, digital traffic management are improving rapidly. Data systems can now support many flights real-time. Regulatory momentum. Many national authorities, including the FAA in the U.S., are shifting from cautious pilot programs to structured approval pathways. Public safety demonstration projects, case studies giving evidence, pressure from crises, pandemics, climate disasters, infrastructure failures all expose how fragile ground-based logistics can be. There is urgency to find resilient alternatives, environmental and social incentives, pressure to reduce emissions, pressure for equitable service, for innovation in urban mobility and delivery, public awareness and early wins. As people see successful medical deliveries by drone or remote platforms getting urgent supplies, the idea becomes more credible, more acceptable. Conclusion: the sky as a new supply chain layer. As we draw toward a close, I want to leave you with the central thesis. The sky is becoming a new layer of logistics, not the replacement of ground transport, but a parallel, complementary set of pathways, sky lanes if you like, that allow speed, resilience, and reach that ground cannot provide alone. Zipline, Volansi, Matternet, Grid Aero, they are pioneering these lanes, each with different missions, different aircraft, different operational styles. Zipline with medical lifelines, Matternet with precise urban corridors, Volansi reaching remote, rugged zones, Grid Aero operating where detection, risk, and adversity are high. For patients, this means treatments arriving on time. For communities, fewer trucks congesting streets and more efficient use of space. For businesses, new service models and competitive edges. For defense and disaster response, agility when it matters most. For the planet, reduced emissions, less waste, cleaner cities if done with care. Picture again that scene. Late afternoon, rooftops, a drone, a parcel gliding gently down, no fuss, no chaos. That image may become as ordinary as seeing a mail truck turning a corner, and perhaps one day we'll scarcely think of it as remarkable, just part of how things get done. The sound of the future, closing reflection. Stand outside at dusk sometime. Listen, the city has its symphony. Tires on asphalt, distant sirens, conversation carried on the breeze. Now listen again. Maybe you hear a softer thread woven into that symphony. The hum of rotors, perhaps. Controlled, precise. A pause. Then silence. That hum may belong to a drone finishing a delivery, lifting off, the sky lane working quietly. We are on the verge of logistics unbound by roads and terrain, by traffic and floods. Each parcel delivered from above is a small testament to human ingenuity. Aircraft and algorithms, regulations and relationships fused together. One parcel at a time, quietly the sky's becoming a supply chain. Thanks for watching, and remember, technology when used wisely can help us protect what matters most. Thank you. I welcome your questions.